In this video, we will continue our investigation into integration by parts. So as a reminder, the typical formula we think of for integration by parts is that the integral of u dv is equal to uv minus the integral of v du. So kind of an immediate observation to make is whatever we choose to be dv needs to be something we can anti-differentiate to find v. And ideally the u, when we differentiate it, will become simpler so that the resulting integral will be easier for us to evaluate. In terms of when we can apply integration by parts, it's typically well suited for polynomials times a cosine or sine, a polynomial times an exponential. And we've previously seen such examples. Additionally, it works really well with inverse functions and things like an exponential times a trig function, sine or cosine specifically. So let's look at a few more examples. Let's evaluate the given definite integral. Now the observation to make here is that what we are integrating is the natural log, which is an inverse function, which should be well suited for integration by parts. So when we use integration by parts, we somehow have to come up with a choice of u and dv. And if we think about this just big picture once again, whatever we let our dv be, we have to be able to anti-differentiate. So if I wanted to set dv equal to natural log x, that would be a particularly poor choice because we don't know what the antiderivative of natural log is. That's what we're trying to find. So really my only choice here would be to let u be equal to the natural log of x. And what that leaves us over with for our dv would be the dx. So we can really think of dv as being this kind of hidden 1 dx. 1 is something we can anti-differentiate, so v would be x. And natural log is something we can easily differentiate, 1 over x. So integration by parts tells us uv minus the integral of v du. So uv would be x ln of x, and we evaluate from 1 to 2. We need to get our limits in there. Then we subtract the integral of v du. Well, when v hits du, it's almost too good to be true here. It's just a 1. And we're evaluating from 1 to 2. So for the first part, we can go ahead and start plugging in those limits of integration. Plug in x equals 2. Put a minus sign, plug in x equals 1. And then evaluate the resulting definite integral. The antiderivative of 1 is x. We need to evaluate from 1 to 2. So kind of just working our way from left to right, we have 2 natural log of 2. Natural log of 1 is equal to 0, so that term goes away. We plug in x equals 2, put a minus sign, so minus a minus is a positive, and we plug in 1. So what we end up with is 2 natural logs of 2 minus 1. So 2 observations to make. When it comes to integrating inverse functions, say natural log, we can apply integration by parts. To do so, we will let our u be the given function, and we'll let dv simply be that leftover 1. Also, for an integration by parts with a definite integral, we proceed exactly as we did in the indefinite case, except we add in those appropriate limits of integration. So we'll now look at a second but very similar example, the indefinite integral of arctangent. Because arctangent is an inverse function, that fits into this category of functions that are well suited for integration by parts. So what we need to do is come up with our choice of u and dv. And remember, whatever we choose for dv needs to be something we can anti-differentiate. So that leaves us having to pick u in this case to be arctangent. And if u is arctangent, as we saw in the previous example, that means dv is going to have to be 1. So du is 1 over x squared plus 1. And v is equal to x. Integration by parts gives us uv minus the integral of v du. So this will be x arctangent minus the integral of v du. So x over x squared plus 1 dx. And now this remaining integral is something that should be simpler for us to evaluate. And the observation that we can make here is that we see an x squared plus 1 in the denominator, and essentially its derivative appearing outside of that function. So that's an indication that we might want to try a substitution. So for the substitution, let's go ahead and set w equal to x squared plus 1. And typically we would say u, but we've already used that variable, so we move on to w. So dw is 2x dx. So the x squared plus 1 in the denominators are w. The x dx left over is going to be 1/2 dw. So we have 1/2 that can be pulled out front, and that would become left over an antiderivative of 1 over w dw. So this really is a reasonable integral for us to evaluate, and keep in mind that we typically may have to apply more than one method of integration. We started with integration by parts, but the resulting integral might require a separate method, here substitution. So we have x arctangent of x minus 1/2 the natural log of the absolute value of w plus c. And our last step is to resubstitute. So the single w that we have needs to be replaced with an x squared plus 1. Note x squared plus 1 is always a positive quantity, so we do not necessarily need the absolute values, but just as a matter of good practice, I will typically leave them. So as we've seen in these last two examples, natural log and now arctangent, integration by parts works extremely nice for integrating inverse functions. Let u be that given function and dv be dx. Let's now look at one last example involving integration by parts. So the exponential e to the x times the trig function sign. As mentioned previously, this is something where integration by parts is well suited. So what we are going to do is come up with a choice of u and dv. And in this case, we can easily anti-differentiate both e to the x and sine, and neither one of them really becomes simpler when we differentiate. So it turns out it doesn't really matter what choice we use for the u and the dv. So I'm just going to go ahead and say u is e to the x, so that dv would be sine x dx. So du is e to the x dx, and v would be the antiderivative of sine, which is minus cosine. Now we apply our integration by parts, so we get uv, so e to the x, and I'm going to pull the minus out front, cosine, minus the integral of v du. And noticing that we have the minus sign, we can go ahead and pull that out and say minus a minus becomes a plus, and v du is going to be e to the x cosine x. And now note at this point the resulting integral is supposed to be simpler for us to evaluate. In this case, it may not be simpler, but it's certainly not more difficult. So let's just kind of go ahead. We've applied integration by parts. There's nothing stopping us from applying a second integration by parts. We may have to apply it multiple times. So let's see here. We have the minus e to the x cosine x, and then a second integration by parts. And I'm going to go ahead and use u and dv again. And as long as we organize our work in such a way that it's clear at what stage we are applying the integration by parts, you're more than welcome to use the same variable. If you have would like to use different variables, you could use u1 and v1. So I'm going to proceed exactly as we did before. We let u be e to the x and dv be cosine x. And I'll mention that if you did this in the opposite way now, if you let u be cosine and dv be e to the x, that would not be a good choice, because what we would do is end up undoing the previous integration by parts. So you want to stick with that choice that we originally made for our u. So du is e to the x, and v would be the antiderivative of cosine, which is sine. So we're now applying our second integration by parts. So we have uv, so e to the x sine x, and we are subtracting away the integral of v du. So we're subtracting away the integral of e to the x times sine x. So just to kind of recap where we are, we would like to evaluate the integral of e to the x times sine x, and it's equal to this. But notice we've ended up with this exact same integral that we would like to evaluate. And kind of an analogous algebra problem is if I have x equals 1 minus x, which I realize looks maybe a bit silly, you would say, oh, add x to both sides, so that 2x is equal to 1, and then we can easily solve that x is equal to 1/2. So we can do the same exact thing here. What we can do is take this integral we have on the right, we can add it over to the left. So what this actually gives us is that we have two integrals of e to the x times sine, and that's equal to the first two terms on the right. So minus e to the x times cosine plus e to the x times sine. And now we can simply divide by 2, and that's going to give us the value of our indefinite integral. So e to the x sine x is equal to 1/2 e to the x, and just kind of pulling out that e to the x, we'd have sine minus cosine. And because it's an indefinite integral, we need to remember to add in our plus c. And as a side observation, if we had started with the integral of e to the x times cosine x, a similar technique could be used. And keep in mind, we may have to use multiple methods of integration to solve a given integral, and it is perfectly reasonable to apply more than one integration by parts.